Today we're going to start into our last unit, which is going to be the physical science unit. To start with, we are going to look at the periodic table and do a bit of a refresher about the areas of the periodic table, and then start to look at some of the really interesting trends which exist due to the order that the periodic table has been put in. We need to review chemical formulas, we need to review what their properties are, and then we'll start to look at trends. When we talk about trends, we look at the size of the atom, which is measured by taking the radius. We're going to look at ionization energy, and we will review electronegativity. Do you remember these three areas of the periodic table?
Yes, except for metalloids.
Okay. Where do you think the metalloids are?
I would think on the bottom.
Nice guess, but not quite.
Huh?
Good guess. First of all, where are your metals?
Metals, everything left of the staircase.
So are they along the staircase?
Braden?
Aren't they like above the staircase?
Metalloids are touching the staircase, yes. Metals are to the left-hand side of the staircase. Non-metals are on the right.
Hydrogen's classified as a non-metal, right? I'm
Very good question.
always confused because it's on the left side, but I believe that it's. I don't think hydrogen would be a non-metal.
And in some periodic tables, you will see hydrogen on the left-hand side of the table, but also on the right-hand side of the table. It most likely acts like a metal in most situations. However, there are a few situations where hydrogen will gain an electron instead of losing its own electron. So the metals are to the left of the staircase line. The non-metals are to the right side of the staircase line. The metalloids are the ones that are on either side of the staircase line. Some properties of metals. They're generally electrical conductors. They do not have the same electrical conductivity. Think about what we use for our wiring.
Copper,
Why?
because it conducts electricity well and is cost efficient.
Okay. Why don't we use one of the best conductors of electricity, which is solar?
Because it's too expensive.
Can you imagine wiring your house with solar? Wow. That would be tremendously expensive. What does it mean to have luster?
It shines.
Yes. Some metals rust very easily, so their shine goes away quite quickly. What about to be ductile?
No,
What do we mean if we say something is ductile?
Ducts are where air flows.
It means that we can draw it into a thin wire.
That's exactly what I thought you was
What about the word malleable?
Bendable, how easy it is to shape.
We can change its shape without breaking it. Non-metals don't allow us to do that very easily. The non-metals are generally very brittle. They don't shine, and they're usually pretty poor conductors. Here is a periodic table on the screen which shows you the substances that are classified as metals, non-metals, and metalloids. Notice that aluminum here, number 13, is actually classified as a metal and not a metalloid. I like to think of metalloids as having a split personality. They have some characteristics of metals, but they have some characteristics of non-metals. For example, silicon. Silicon is used in computer chips. If silicon was not conductive, we wouldn't be using it in computer chips. In this case, hydrogen is being marked only as a non-metal. This can be a little bit misleading because hydrogen can be classified as acting like metal and losing an electron. However, it doesn't usually have metallic properties like being shining or good conductor, etc., because it's a gas at room temperature. Some nonmetals are gases. These are marked yellow on my periodic table up here. Sulfur is an example of a nonmetal that is solid at room temperature, and it is a bright yellow color. There's only one liquid in the nonmetal area: bromine. The metalloids, as I mentioned before, are on either side of the staircase. They have intermediate properties, and they're either semiconductors or moderate conductors that heat electricity, depending on the situation. Each periodic table varies. What information do we have on our periodic tables that is not shown in this information square?
Most stable ion charges.
Okay, ion charges are not shown in the slide. What
Their
else?
ability, electronegativity.
Electronegativity. One of the reasons why I chose the table that I did was because it had the electronegativity, which I think is very important to see. Some tables will have melting points and boiling point information. Rather than doing that, there is a separate page in the back of those data booklets which has melting point and boiling point information. I think that keeps more information off of the table, which means we can use a larger font for the information that is on the table.
Oh, we can't.
We do not have electron levels represented in ours because you know how to find electron levels. We've been doing that since grade 11, or grade 9 actually. It was the first time we did a Bohr model. Group 1A, do you remember talking about alkali metals?
Yes. I don't remember what they are.
Aren't they in like the first or second row?
First area, or sorry, first group. Up, down, which is a column.
They are.
Except for hydrogen. Hydrogen up here is not considered to be an alkali metal. But all of these are. Do you remember any of the properties of an alkali metal?
They're earth metals?
Pardon me?
That's group 2.
Oh.
They are.
Oh, you don't remember this video? Okay, I have to
You
recall
can eat
this
them and
video
they'll
up
die.
here.
Can they be used in batteries?
True. Wait, we need Frampton?
I know. But you use a test them.
Oh yeah, they explode in water.
One property of alkali metals is that they are extremely reactive with water. The reaction of water produces hydrogen gas. If there is a spark or anything but hydrogen gas will ignite and go boom. Did you notice the two metals in the pill-like container?
Yeah.
What color?
Gray.
So gray color. Were they shiny or not shiny?
Not shiny.
They're very shiny.
No.
Until they're exposed to air, the water moisture in the air is enough to react with those things. When the alkali metals are stored, you have to store them under kerosene, which is a thick, heavy petroleum product, so that it doesn't combine with any water moisture in the air. Group 2A. These are your alkaline earth metals. Do you remember some things about alkaline earth metals? Oh,
They're also reactive with water?
not nearly
Well, not
as much as group 1 is. They will dissolve if they're with a hydroxide. So if I have something like calcium hydroxide or magnesium hydroxide, those will dissolve in water to form a basic solution. Think of some of your antacid products. All of those things are actually made up of alkaline earth metals. They can be gray. They're usually associated with something else. Do you remember the noble gases? Yeah. What do you remember about the properties of a noble gas?
Okay.
The name gives something away.
Everyone wants to be with a noble gas or be a noble gas or something like that.
Why?
Because I think they have all their electrons to match up.
Yes. They have completely filled energy levels, which makes them very stable. They used to be called the inert gas family because inert means to not react. If we put those things under a high enough temperature and high enough pressure, we can force them to form compounds, but it's extremely rare. They're all gases at room temperature. Then we have the group 7A, or 17. These are the halogens such as fluorine, chlorine, iodine. These are all very reactive. You cannot generalize state of the halogens. 2 of them are gases, 1 of them's a liquid, 2 of them are solids, 117, we don't know. It lasts for a short period of time, so it's hard to determine the state of it. The ones that are gases tend to be colored. The chlorine gas
Yellow.
gets its name mustard gas because of the yellow color that it has. Iodine is purple. When it sublimates into a gas, it will be a purple gas. Bromine is kind of a brownish color.
That'd be so pretty.
So in review, alkali metals, they are extremely reactive with water, and the reason is they have 1 valence electron. Do you remember what a valence electron is?
They have their second ring full, and they have 1 alone on the
Mhm.
ring.
For example, sodium. Sodium has how many protons?
11.
That was terrible. Shoot. Yes.
Okay, this isn't working. If I have 11 protons for sodium, I have 2 electrons in the first energy level, 8 electrons in the second energy level, and 1 electron in the last energy level. The electrons in the last energy level are given a special name, and they are called valence electrons.
Yep, that's the complete design of this.
If you take a look at potassium, it has 19 protons, which means we have 2 electrons in the first energy level, 8 electrons in the second, 8 electrons in the third, 1 electron in the fourth energy level. It also has 1 valence electron.
So the first level can only hold up to 2 electrons, right?
Correct.
And then the next 2 can, and then all the rest can only hold 8.
Oh, this is
No. Period 2 and 3 can go up to 8. Period 4 and 5 can go up to 18. Periods 6 and 7 go up to 32. That is using Bohr structures. In order to figure out how many electrons go into each level of the Bohr model, you count across. Here you have to remember that 57 to 71 is down here. You're actually going to be learning a new model in this unit called the quantum mechanics model. That will change how you represent atoms. Alkaline earths all have 2 valence electrons. Calcium, for example, has 20 protons. What is electron level structures going to look like?
2, 8, 8, 2.
2. So 2, 8, 8, 2. Those 2 electrons in the last level can be lost in order to have a structure similar to a noble gas. It's still reactive, but nowhere near as reactive as the first group. Halogens, they have 7 valence electrons, which means they're 1 electron away from a full energy level. Rather than gaining 7, rather than losing 7 electrons, gaining 1 allows it to fill its electron level needs. These are all very toxic and they are reactive. And finally, the noble gases are the ones that have full electron shells in their Bohr model. They're kind of the it group of the periodic table. Things want to have full energy levels. Questions?
Wait,
Mm-hmm.
so are like chlorine gases excluding that? Are all the halogen gases toxic?
Yes. They're very hazardous to human health, even in very small concentrations.
So like even something like for example iodine, like the purple gas, that's highly toxic.
Yes.
That doesn't mean arsenic.
Other questions?
I got you.
You did get me there.
It's a little bit of a review of the last 4 years of chemistry. Hopefully it's making a little bit of sense.
That is so cheap.
I was hoping for a few smiles. Thank you.
What's wrong?
What we're going to do is look at patterns. A pattern is a trend. The first periodic pattern that we're going to look for is atomic size. We want to be able to look at patterns and the ability to gain or lose an electron as indicated by ionization energy and electronegativity. All periodic table trends are influenced by 3 factors. First, energy levels. Energy levels are those orbits that are around an atom. For example, if we look back at our model of sodium, this is our first energy level, this is our second energy level, and this is our third energy level. When we say higher energy levels, that means that it is further away from the nucleus. Why do you think energy levels might matter in determining the properties of an atom?
The further away it is from the nucleus, it might be easier to lose an electron.
Yes. The further away from the nucleus it is, the easier it is going to be to remove from a particular level. Remember that atoms are held together because of charge attraction between the protons, which are in the center of the atom, and the electrons, which are found around the atom. The stronger pull that occurs, the harder it is to take electrons away. The number of protons will also influence a periodic trend. The reason is the protons are the positive pole of the center of the atom. The more charge you have, the more attractive force you have. Energy levels have an effect on the group. Nuclear charge has an effect on the area. When we talk about atomic radius is from the outer edge of an atom to the middle. Look at what happens to the atomic radius as we go down a group. We start with hydrogen, then we go to lithium, sodium, potassium, and rubidium. What's happening?
They're getting bigger.
Why?
Each are gaining more, or is gaining more energy.
Nope. Why would those atoms physically be getting larger?
Because
As we go down a group.
Because
they get
the
more and more rings.
Yes, they get more orbits. For example, if we draw out the Bohr models, starting with hydrogen. Hydrogen has one proton and one electron. Lithium has 3 protons and 3 electrons. If we look at the Bohr model, there is another orbit. If we go down to sodium, sodium has 11 protons and 11 electrons. And here we have 3 shells. As you add another shell of electrons, the atom becomes larger. Looking across here, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and iron. What is happening to the size? It's getting smaller. Why do you think atoms would be getting smaller as it goes across a road or a period? Spencer?
The nuclear charge is decreasing.
Yes. Because you have more protons, you have more attractive force, it's going to pull in the electrons with a stronger force. If I add another proton, more internal force, which is going to pull the electrons in even closer. By the time we get to argon, which has 18 protons compared to sodium that has 11 protons, 18 protons has far more of an attractive force in the center of that atom. examines the atomic radius of different atoms in the periodic table. Take a moment with that graph. See if you can determine a pattern. We have hydrogen here, lithium, sodium, potassium, rubidium. As we go down a family, the atomic radius increases. As we go from lithium across the road to neon, the atomic radius decreases. As we go from sodium to argon, the atomic radius decreases. A bit of a blip going on here. It follows the same pattern as the first three rows, and then all of a sudden you have an abnormality right here. You have an abnormality right here too. Any suggestions?
Because the krypton is pulling closer to the potassium.
Sorry, I can't hear you.
I'm wrong, but because the krypton is pulling closer to the potassium, so it's bumping.
Why would an atom become larger?
Energy levels?
Because it's gaining another ring. I don't know.
I think it's why would one thing be larger than another?
There's more
Either
of it.
has more electrons
Or
or less pull between the nucleus and the electrons. So something's happening 3/4 of the way across a period that results in less attraction between the protons and the electrons. What's going on here is not something that can be shown in a Bohr model. You have to use electron configurations of the quantum mechanics model to understand why there is a blip in the map in that fourth and fifth period. Okay. Which one should be the larger of the two? Calcium or strontium?
Strontium?
Sorry, you said which one?
I said strontium.
Yes. When you go down a group, things get larger. Magnesium here, or nickel over here.
Nickel,
Why?
because it has a larger atomic number and is lower than it.
It's in the next.
Yeah, like
Period.
it's called. Periods.
But as we go across a row, what happens?
Decreases.
It becomes smaller. So actually, this is a very tough question to answer based on just an introduction to this. I would predict that nickel might be slightly larger than magnesium, but not tremendously larger.
It's manganese.
Manganese, okay. Manganese versus nickel.
Oh,
Which
that
one's
changes the
larger?
question.
Manganese.
Manganese is nitrogen or oxygen.
Nitrogen.
Nitrogen will be the larger of the two. Zinc or cadmium.
Cadmium.
Cadmium should be a lot larger. The rule is, as you go down the group, the atomic radius increases. As you go across a period, the atomic radius decreases. I'm going to give out a practice sheet.